Okay, continue on physical chemistry, chapter 12, section 3. We're going to be talking about two more colligative properties now, the freezing point depression and the boiling point elevation. Now let's say we have the partial derivative of the Gibbs free energy, the molar Gibbs free energy, of substance I, that's our solute, with respect to temperature holding pressure constant. Remember, that's equal to the chemical potential of the substance I with respect to temperature holding pressure constant. And that is equal to minus the molar entropy of substance I. Now, remember, the differential of the Gibbs free energy is equal to minus entropy times the differential of temperature plus volume times the differential of pressure. Now, we're talking about constant pressure, so we're going to say that dG, the differential of the Gibbs free energy, is just equal to minus entropy times the differential of temperature. So then we have the partial derivative of the Gibbs free energy with respect to temperature holding pressure constant is just equal to minus the entropy. Okay, now here we have the chemical potential of pure water versus the freezing point temperature. So as you increase the temperature here, the chemical potential is going to go down. So at the solid phase to liquid phase, that's the freezing point, there's going to be a change in slope, and then it's going to go down some more, and then when we go to the boiling point, from the liquid phase to the gaseous phase, the slope's going to go some more. So the slope is going to be equal to minus S, because that's what we're graphing here. So the temperature at the freezing point star, that's the freezing point of the pure substance. So at the freezing point, we say the chemical potential of the solid is equal to the chemical potential of the liquid, because they're in equilibrium, they're at phase equilibrium, and that's called the melting point. And likewise, TB star, that's the boiling point. At TB star, the chemical potential of the liquid of the pure substance is equal to the chemical potential of the gas of the pure substance. And of course, that's the boiling point. Now, if we're in the solid region on that graph, which means the temperature is below the melting point, then the chemical potential of the solid of the pure substance is less than the chemical potential of the liquid of the pure substance, which means the solid is more stable. Liquids have higher entropy than solids. Now, in the liquid region, between the melting point and the boiling point, then obviously the chemical potential of the liquid of the pure substance is less than the chemical potential of the solid of the pure substance. And then likewise, in the gas region, which means we're above the boiling point, the chemical potential of the gas of the pure substance is less than the chemical potential of the liquid of the pure substance. So as temperature increases, entropy increases, so the slope gets more negative, which, looks steeper. Okay, here we go again. That's a similar graph. So again, we're doing a chemical potential of the substance A, which is water, the pure substance. And this is potential versus temperature. So here we go. The solid lines, I said, are the pure H2O. So this is the line for solid, this is the line for liquid, this is the line for gas. Now if we add some solute, the line's going to shift, namely this one for the liquid region. So we have the temperature of the freezing point star, pure. The temperature of freezing is going to go down because it'll intersect this line farther to the left. And likewise, the boiling point pure substance, it'll increase because this line will intersect farther right. So the temperature of the freezing point star goes to temperature freezing, that's freezing point depression, and the temperature, the boiling point of the pure substance goes to temperature boiling, that's boiling point elevation. Now adding solute doesn't change the slope of the graphs. All it does is it shifts the line. Now the freezing point moves left, which is depression, and then the boiling point moves to the right, that's elevation. Now remember, this boiling point elevation though is not caused by energy. It happens even when the change in enthalpy of mixing is equal to 0. And remember, we said before anyway that the change in enthalpy for mixing is equal to 0 for an ideal solution anyway. And we said on that equation on the previous page, it's caused by the entropy. Now adding solute increases the entropy of the solution, which means that there is less reason for the solvent in the liquid phase to escape into the vapor phase. Now the change in temperature of freezing is usually larger than the change in temperature of boiling, since the solid curve has the lowest slope. And like I said already, the colligative properties are from entropy. The chemical potential of the substance A is equal to the chemical potential of the pure substance A plus the gas constant R times the absolute temperature times the natural log of the mole fraction of substance A. Now the mole fraction of A is equal to 1 if you have pure solvent, and obviously it's less than 1 if you've added some solute. And of course the temperature is greater than 0, and the natural log of the mole fraction has to be less than 0. So from that formula, you know the chemical potential of the substance A has to be less than the chemical potential of the pure substance A. And remember, the chemical potential of the pure substance A is constant at a given temperature. Now for an ideally dilute solution, this line means molar, remember. So the molar enthalpy of substance A is equal to the molar enthalpy of the substance A, a pure substance. And the molar entropy of the substance A is equal to the molar entropy of the substance A in the pure substance plus the gas constant R times the temperature times the natural log of the mole fraction of substance A, where the mole fraction or the molar entropy of substance A is greater than 0. So mu A is equal to the molar enthalpy of substance A minus temperature times the molar entropy of substance A. And remember that molar entropy of substance A is positive. So mu A decreases. Okay, now we're going to derive the formula for freezing to point depression. Now we're going to start by assuming that only pure A, the solvent, freezes out when the solution freezes. For example, in the ocean, salt water, when the water freezes, the icebergs are pure water. They're not salt water. So we have mu sub A, the chemical potential of A in the solution, is equal to the chemical potential A of the pure substance in the solid form, because they're in equilibrium. And this S means solid here. So mu A of the solution is equal to mu A pure substance in the liquid phase plus RT natural log of the activity of substance A. And this L here means liquid. So the chemical A of the solution is equal to the chemical potential of A in the liquid phase of the pure substance plus RT times the natural log of the activity of A. Now remember, the activity of I is equal to the activity coefficient of I times the mole fraction of I. Now we said the activity coefficient of I is equal to 1 if you have an ideal or an ideally dilute solution. Now the chemical potential of substance A in the liquid phase, when it's pure, plus the RT times the natural log of the activity of A is equal to the chemical potential of A in the solid phase, when it's pure. So the chemical potential of A in the liquid phase, pure, at whatever the freezing point temperature and whatever pressure, plus R times the freezing point temperature times the natural log of the activity A, is equal to the chemical potential of A, and for the solid phase, pure, at the freezing point temperature and pressure. And remember, with pressure, we're just saying 1 atmosphere for now. Now the natural log of the activity of A, then, is equal to the molar Gibbs free energy of the solid stuff of A in the pure form at the freezing temperature, minus the molar Gibbs free energy in the liquid phase of the pure substance at whatever temperature, freezing point temperature, divided by R times TF. Now remember, the chemical potential of the pure substance is equal to the molar Gibbs free energy of the pure substance. For solid in equilibrium with liquid, in other words at the freezing point, then the change in Gibbs free energy of fusion, remember what we call melting, fusion, not nuclear fusion, molar of substance A, is equal to the molar Gibbs free energy, substance A in the liquid phase when it's pure, minus the molar Gibbs free energy of substance A in the solid phase. Now, from the Gibbs equations, we know that the partial derivative of Gibbs free energy of the pure substance with respect to temperature holding pressure constant is equal to minus the entropy of the pure substance. So that works for deltas too. So we get the partial derivative of the change in the molar Gibbs free energy with respect to temperature holding pressure constant, and that's equal to minus the change in molar entropy. Now, using the product rule, we get the partial derivative of the natural log of the activity of A with respect to the freezing point temperature holding pressure constant is equal to the partial derivative of this whole quantity, the change in the molar Gibbs free energy of fusion of substance A at whatever temperature with respect to freezing point temperature, times 1 over R times the freezing point temperature, plus the partial derivative with respect to temperature of 1 over temperature times the change in the molar Gibbs free energy of fusion of substance A at whatever freezing point temperature divided by R. So we get the partial derivative. Oh yeah, so calculus, just rearranging the equation, we use partial derivative with respect to temperature of freezing of 1 over the temperature of freezing is equal to minus 1 over the temperature of freezing squared. So we get the partial derivative with respect to temperature of freezing of the molar Gibbs free energy of fusion of substance A at temperature of freezing, is equal to the minus the molar Gibbs free energy, or minus the entropy of fusion of substance A of the freezing point temperature. So we get the partial derivative of the the natural log of the activity of A with respect to the freezing point temperature holding pressure constant is equal to the change in the molar entropy of fusion of substance A at whatever freezing point temperature divided by R times the freezing point temperature, plus the change in molar Gibbs free energy of fusion of substance A at the freezing point temperature divided by R times Tf squared. Now we want that equation with a common denominator, and then we want to split out the the Gibbs free energy into enthalpy and entropy. So we rewrite it. The partial derivative of the natural log of the activity of A with respect to the temperature of freezing, holding pressure constant still, is equal to this quantity here, the temperature of freezing times the molar change in entropy of fusion of substance A at the freezing point temperature, plus the change in molar enthalpy of fusion of substance A at the freezing point temperature, minus the temperature of freezing times the change in the molar entropy of fusion of substance A at the temperature of freezing. All that over R times the temperature of freezing squared. Now, you notice these two cancel out, so we're left with just the partial derivative of the natural log of the activity of A with respect to temperature of freezing at holding pressure constant is equal to the change in enthalpy, the molar enthalpy of fusion of substance A at the freezing point temperature, divided by R times the temperature of freezing squared. Notice how that looks kind of similar to the Van 't Hoff equation that we learned about in Chapter 6, which was the derivative of the natural log of Kp naught with respect to temperature is equal to the change in enthalpy of the standard state divided by RT squared. Now we have the differential of the natural log of A is equal to the change in the enthalpy of fusion, the molar enthalpy of fusion at temperature of freezing point temperature, divided by R times the temperature of freezing squared, times the differential of the temperature of freezing. Then we want to integrate that. So we have the integral from state 1 to state 2 of the differential of the natural log of the activity of A is equal to the integral from state 1 to state 2 of the change in molar enthalpy of fusion of substance A at the freezing point temperature divided by RTF squared with respect to TF. Now remember, state 1 is going to be our pure A. So the temperature of freezing of 1 is equal to the temperature of freezing star. And the activity of A at state 1 is just going to be equal to 1. Now state 2 is whatever general state with a solute added. So we'll just say that TF2 is equal to TF, and then the activity of A at state 2 is just the activity of A. So we're going to rewrite that equation so it makes more sense. So the natural log of the activity of A at state 2 minus the natural log of the activity of A at state 1 is going to be equal to the integral from state 1 to state 2 of the change in molar enthalpy of fusion of substance A at the temperature of freezing divided by R times the temperature of freezing squared with respect to the temperature of freezing. So we can combine those two on the left and we'll get the natural log of the activity of A2 at state 2 divided by the activity of substance A at state 1, and that's equal to the integral from state 1 to state 2 of the change in the molar enthalpy of fusion of substance A at the freezing point temperature divided by R times the freezing point temperature squared with respect to the temperature of freezing. Now since we're talking about the freezing point, we wrote temperature of freezing as a dummy integration variable. But it can be whatever temperature, so we're just going to call it T from now on to simplify a bit. So we're going to use activity. Remember, the activity of A is equal to gamma of A times chi A. So let's say we have two components, A and B. Remember, chi A then would be 1 minus chi B. Now that of course means there's no dissociation of B and no association of B, which of course means that B is not an electrolyte. So we have the natural log of the mole fraction of A times the activity coefficient of A equal to the natural log of the mole fraction of A plus the natural log of the activity coefficient of A, and that's going to be equal to the natural log of 1 minus the mole fraction of B plus the natural log of the activity of A. So we're going to use a Taylor series to expand that term. Okay, I can't read my handwriting. So chapter 8 talks about I see, that's natural log of y. So we're going to use a Taylor series to expand the natural log. Chapter 8 is when it talks about Taylor series. So if we're talking about the natural log of y and it's approximately y is equal to 1, then what we have is that natural log of y is written as y minus 1 minus y minus 1 squared over 2 factorial plus y minus 1 cubed over 3 factorial minus y minus 1 to the 4th over 4 factorial, etc. Now, let's say that y is equal to 1 minus b. Well, then the natural log of 1 minus b is going to be just equal to minus xb over minus x over b squared over 2 factorial minus x over b cubed over 3 factorial minus x over b to the 4th over 4 factorial, etc. And that's only if we have an ideally dilute solution, then the mole fraction of b is much, much less than 1 though. Okay, so now we have the natural log of the gamma of A is equal to b2 times xb squared. This b is some coefficient that's dependent on temperature and pressure. And then b3 of xb cubed, etc., etc. And this is from statistical mechanical theory of solution. Now the derivation of that is beyond this class, but we're only going to use this first term anyway to simplify. So the natural log of the mole fraction of A times the activity coefficient of A is going to be equal to the integral from the temperature of freezing point pure to the freezing point of the change in the molar enthalpy of fusion of substance A over RT squared with respect to T. And then the natural log of gamma A, chi A, is going to be equal to minus xb, or chi B, plus b2 minus 1/2 over xb squared, etc. Now we know that chi b is very small, so xb cubed or chi b cubed or squared is much smaller, and each term will get smaller and smaller and smaller. So we're just going to use the first term. So like b2 minus 1/2 is roughly equal to 0. So what that means is we could just write it as the natural log of the activity coefficient of A times the mole fraction of A is roughly equal to minus the mole fraction of B. Now the mole fraction of B minus the mole fraction of B is equal to the integral from the freezing point temperature of the pure substance to the freezing point temperature of the change in molar enthalpy of fusion of substance A at whatever temperature divided by RT squared dt. And remember, enthalpy is temperature dependent. So we're going to have minus chi B is equal to the change in molar enthalpy of fusion of A divided by R. Okay, so we pulled this out, assuming it's constant. Times the integral from the freezing point temperature of the pure substance to the freezing point temperature of the solution of 1 over T squared dt. And that's going to be equal to delta H molar of fusion of A divided by R. That integral is minus 1 over T evaluated from TF star to TF. So that gives us minus chi B is equal to the delta H molar fusion of A over R times 1 over TF star minus 1 over TF. Or you can rewrite that with a common denominator and you'll get the change in enthalpy, the molar enthalpy of fusion of substance A over R. It's going to be TF minus TF star divided by TF times TF star. So the freezing point temperature of the solution is close to the freezing point temperature of the solvent. So TF is close to TF star. So we could say that TF star times TF is roughly equal to TF star squared. So if TF is equal to TF minus TF star, oh no, the delta TF, the change in the temperature of fusion is going to be the change in the temperature of fusion minus the temperature of, no, it should be temperature of fusion of the pure substance. And that's going to be less than 0 because we're talking about freezing point depression. So the change in temperature of fusion is going to be equal to minus the mole fraction of substance B, our solute, times R, times the temperature of freezing of the pure substance squared, divided by the change in enthalpy, the molar enthalpy of fusion of substance A. Now, chi B, the mole fraction of B, is equal to the number of moles of substance B divided by the number of moles of substance A plus the number of moles of substance B, because we're talking about only two substances. Since Na is so much bigger than Nb, we can just say that, approximate that by saying Nb divided by Na, because Na plus Nb is roughly equal to Na, since we're talking about an ideally dilute solution still. Now, the molality of substance B is the number of moles of substance B divided by the number of moles of substance A times the molar mass of substance A. And remember, that's molality is in moles per kilogram, and the molar mass is going to be in kilograms per mole. Then the number of moles of substance B is equal to the molality of substance B times the number of moles of substance A times the molar mass of substance A. And the mole fraction of substance B is going to be the molality of substance B times the number of moles of substance A times the molar mass of substance A divided by the number of moles of substance A. Notice these two will cancel out. So, based on that approximation we made, the mole fraction of substance B is just the molality of B times the molar mass of substance A. Now the change in freezing point temperature is going to be equal to minus the molality of substance B times the molar mass of substance A times R times the freezing point temperature of the pure substance squared divided by the molar enthalpy of fusion of substance A, the change in the molar enthalpy of substance A. Now, we're going to say Kf is the molal freezing point depression constant, also known as the cryostatic constant. So we're going to have the Kf is going to be defined as the molar mass of substance A times R times the freezing point of the pure substance squared divided by the change in the molar enthalpy of fusion of substance A. Now, the change in temperature of fusion is going to be equal to minus Kf times the molality of B. Now, for water, Kf is going to be 18.0 times 10 to the negative 3 kilograms per mole times 8.314 joules per mole per Kelvin times 273.15 Kelvin squared divided by 6007 joules per mole. So we get 1.86 kilograms per mole. Now, what if we have more than one solute? Then the change in temperature of fusion is going to be equal to minus Kf times the sum over I of all substances not equal to the solvent of the molality of the substance I. So this is all you're adding up all your solutes. So you just add up all the solutes, not the solvent though, of course. The molality is of I, M subscript I is the molality of the solute I. And again, we're talking only about non-electrolytes. Okay, so let's talk about boiling point elevation. The change in temperature of boiling is going to be equal to Kb times Mb. So remember, B is your solute, B is boiling. This B is boiling. So the change in boiling temperature is going to be equal to the temperature of boiling minus the temperature of boiling of the pure substance. So this is solution, solvent. So for H2O, Kb is equal to 0.52 Kelvin kilograms per mole. Now the change in temperature of boiling is usually much less than the change in temperature of freezing. So if you want to find the molecular weight using freezing point depression, it's actually a lot more accurate than if you were to try to do the same thing with boiling point elevation. And that is the end of section 3 of chapter 12.